All right, everyone, welcome to the Andreev Reflection in Quantum Hall Systems workshop, which we have affectionately abbreviated as the ARC workshop. This has been organized by Anton Akhmarov, Christian Schonenberger, and myself, Vala Fatemi, in order to gather scientists interested to discuss the mysteries of the experiments that have been published over the last several years. We're excited to have Carlo Beenakker to introduce the topic area, as well as representatives from 3 leading experimental teams to describe their data. Following all these talks, we will have a panel discussion moderated by Anton. So a bit of logistics. During the talks in the first half, you may pose questions in 2 ways. The first is in the Zoom chat, and we will have a team who will gather the questions to be posed on the panel discussion. The second is to directly contribute a question to the HackMD document that will be posted shortly in the chat. And since we're on a tight schedule, I may transmit a few brief clarifying questions during the talks. And as well, for those of you who have watched the satellite talks, we encourage you to submit any questions related to those as well. And even if you don't have a specific question, but maybe only a comment or a remark, please also do share those in the chat. This is because we will compile a summary of the discussion that will eventually be published, and we will do our best to include all contributions to that. So without further delay, we'll begin with Carlo's introduction to the search for chiral Andreev edge states. Go ahead, Carlo.
Thank you. Yeah, this works. So yeah, it's a search with some prehistory. This is almost 25 years. This was the paper you see here was one of the very first papers, 1998, perhaps even the first paper, where Takeyanagi, who has a long history of being interested in Andreev reflection, pointed out that yes, if you have Andreev reflection of a hole in a magnetic field, then the skipping orbit of the electron will not move back. The hole will continue moving in the same direction. Qualitatively speaking, you could say, well, yes, there's the cyclotron motion, but the charge changes, the mass changes sign, and so the cyclotron frequency, EB over m, remains the same. And so a skipping orbit, which rotates clockwise, like here, if it's an electron, if it's Andreev reflected to a hole, it will still continue to run clockwise. And in this way, you could very well imagine this thing which we now call Andreev edge modes. So electrons and holes alternating at each Andreev reflection and skipping along the boundary. Of course, there is the issue that you would need a strong magnetic field for that, and the superconductor should be able to support that strong magnetic field. And so in these early experiments, the superconductor typically was niobium nitrate, and the semiconductor, which would have a strong proximity effect, was one of these semiconductors with a surface inversion layer, indium arsenide, where somehow the 2d electron gas is on the top of the material, and so it can easily have a strong proximity effect with niobium. As many of you who have been working in this business for decades, which includes me, unfortunately, gallium arsenide is just miserable for this. No good has come out of proximity effect in gallium arsenide. So indium arsenide, with all its difficulties, was the material of choice, let's say, in the 1990s. And this, I think, is a bit later experiment. Ulrich Zülike, a theorist, was very much influential in developing this field in the 1990s. This is actually a paper from 2005 where he collaborated with experimentalists. And they showed this experiment, which I think is very convincing and clear, that if you just plot the resistance as a function of magnetic field, and you go to low enough magnetic field so that the material becomes superconducting, so the proximity effect is operative, then you see that oscillations, fluctuations, oscillations in the resistance basically have much larger amplitudes the moment the material becomes superconducting. And I think these plots are completely clear, and there's no ambiguity here. And the explanation is kind of simple. There are many edge modes here. These are relatively weak magnetic fields. There are many edge modes here, and it's chiral motion, so you would not expect the resistance to oscillate at all, except perhaps for the last innermost Landau level, which might have some backscattering probability. So here, basically, you would be seeing oscillations of one single mode, but there are many more modes, but the other modes do not backscatter. But the moment the thing is superconducting, then there's another mechanism which is not backscattering, but which could change the current, which is electron to hole conversion. And of course, if the electron is converted to hole, that changes the sign of the current. And so all these edge channels can contribute, and you would expect to see basically a much enlarged oscillation, because simply all the edge channels can contribute to this current. Keep in mind that in all these experiments, the superconductor is grounded, so there's no conservation of current. So even a chiral mode may not transport units of current. It could transport even zero current if all the current is just drained to the superconductor. Now, all of this was, of course, in the low field regime. So where you can think, it makes sense to think in terms of skipping orbits. And let's say the 21st century, which is our century, is where we try to somehow generalize this or extend this to the quantum regime where there's only a single lambda level occupied. And for that, something very good happened to many of us, which is graphene arrived around 2005. And graphene is really the dream of mankind. First of all, graphene has a very strong proximity effect. Basically, all experiments succeed immediately. You put a superconductor on top of graphene and you can see Andreev reflection, you can see a supercurrent. It just works like a charm. That's one. And two, graphene can have a pretty large and well quantized quantum Hall effect at low fields. This is mainly because the lambda level spacing grows like square root of B in graphene instead of like B. And yes, square root of B increases less rapidly than B if you're at large B. But in our world, we're always at low magnetic fields. So then the square root rises much more rapidly. And so you can have, basically, even at room temperature, you can have a pretty decent quantum Hall effect. And in particular, that's most important here. Of course, at low magnetic fields, say below 1 Tesla, you can have a singly occupied lambda level. So that's good. So basically, graphene is what everybody jumps to. And yes, I'm a theorist, but with Anton Akhmerov, we tried to do some initial calculations. This is 2006, so ages ago. I had to refresh my memory, completely forgotten. And it turns out, and this is actually kind of neat, as we all know, graphene has 2 valleys, and the valleys are each other's time reversal partner. And so when Andreev reflection, which converts basically an electron into its time reverse partner, Andreev reflection switches valleys. That's one thing to keep in mind. And the other thing to keep in mind is that in graphene, the lowest lambda level is valley polarized. So the lowest lambda is fully within a single valley. And so in particular, the most obvious geometry, which is geometry shown here, we just take the edge of graphene, whether it's zigzag or armchair, doesn't matter, and you put a superconducting contact on that, an electron coming in will always get out as an electron because there's only one valley available. And so the valley switching process, which is required for Andreev reflection, is inhibited. So no Andreev reflection here. The conductance of this object is just zero. The 2-terminal conductance, if I try to send a current from the normal contact into the superconductor contact, it's impossible because Andreev reflection is fully suppressed. So you need to have, and in fact, this is the formula. The formula is kind of like very simple. The 2-terminal conductance is 2e squared over h. And then it's 1 minus the inner product of the valley isospin. There's this representation of valley polarization where, let's say, the north pole is one valley, the south pole is the other valley. And so these are vectors on a Bloch sphere, if you wish, which describe the valley polarization. And so in this case, nu1 equals nu2, so there's 0 here. In the case of 2 zigzag edges, or in this particular example, this drawing here, 2 armchair edges which differ by a multiple of 3 honeycombs, then nu1 is minus nu2, so there's a factor of 2 here, which gives you 4e squared over h. And there's even an intermediate case where you go from armchair with let's say an even number of a number of hexagons, which is not a multiple of 3, and then nu1 dot nu2 is 1/2, and so then you get e squared over h. So you can get different quantum numbers, which is kind of neat. This is a 3-terminal or 2-terminal geometry. The experiment, which we'll see in one of the talks in just a moment by Finkelstein, it's a 3-terminal geometry, so it looks a little bit different. 3-terminal geometry, 1-terminal, 2-terminal, 3-terminal, and then the current I2 divided by V1, so it's, say, a non-local 3-terminal conductance, is also 2e squared over h, but it's nu1 dot nu2 instead of 1 minus nu1 dot nu2. And so if you would have like two zigzag edges, like here, one zigzag edge, other zigzag edge, nu1 dot nu2 is -1, so you would expect minus 2e squared over h. Now, the bottom line here is these are all quantized conductances, which is kind of unexpected. So if you think about skipping orbits, you would say electron becomes hole, becomes electron. Could be anything. No, the valley polarization here ensures that the conductance is quantized. So what is the experiment? So here's the experiment, and I'm sure Gleb will tell you more about this. Neat experiment. It's basically this three-terminal geometry, and you see no quantization, which is puzzling. So there's some resistance, and this three-terminal resistance, they call it RXX here. It's the one which I called I2 over V1 before. So these are irregular fluctuations. This is in the newest 2 Andreev edge mode. So 1 spin degenerate Landau level, and you would expect some number like mine. Actually, you would expect here minus 2e squared over h as conductance, but you don't see that. You see all kinds of fluctuations. And this was, I think, explained quite convincingly by Anton Akhmerov and his group. Antonio Manesco is actually also in the audience. I saw him, and actually all authors, I think, are in the audience. And they noticed that interface disorder plays a big role here. And this is a computer simulation where so this is, let's say, gate voltage that will be this axis. That's the chemical potential. There's magnetic field here, and there's a color plot. But it contains similar information as here, and you can see indeed, random fluctuations between plus and minus e squared over h, plus or minus 2e squared over h, all due to this interface disorder. If they run the same simulation with a clean interface, then it's just quantized and there's nothing. So yeah, this is a bit, I think it's a good result. It's also a bit disappointing that apparently in the quantum Hall effect, where we would hope to see nice quantized universal things, disorder plays such an important role. That is, that's something to work on, because this is not very much fun if you're interested in universal effects. So I've been speaking now for 12 minutes. I think I can use another 3 or 4 minutes to give you a little bit of an outlook of what I think would be, something to go beyond this. Yes, that's this thing here, right? So this is all Andreev reflection. We know about Andreev reflection, and yes, it's kind of interesting to see Andreev reflection in a quantum Hall edge state. But could we actually have a supercurrent carried by this Andreev edge mode? So could a chiral Andreev edge mode carry a supercurrent? That is, I think, a really fundamental and beautiful question. And it's also an old question. It was first raised by Mayans Yuzin. Oh my goodness, 1993. I arrived in Leiden in 1993. This is almost 30 years ago. And so it's a question which has been with me for 3 decades. And the answer is yes, they can. So chiral Andreev edge modes can carry a supercurrent. And it would be kind of an unusual effect. And this is a geometry where I try to explain this. So this will be, you would need 2 superconductors, obviously, 2 superconducting terminals. And then there will be this edge mode here. And the edge mode would circulate around, and it would carry a non-zero persistent current from one terminal to the other. And now there are 2 types of flux periodicities to consider. I imagine this object here being inside a squid ring, some flux bias, so something which biases basically the phase difference between S1 and S2. Now we're very much attuned here to this thing which we call the 4-pi periodic Josephson effect, the 4-pi periodic Josephson effect of Majorana zero modes. First of all, these are Majorana fermions, absolutely. In this system, we have a supercurrent carried by Majorana fermions. Still, this does not show the 4-pi periodic Josephson effect. The Josephson effect has just the usual h over 2e periodicity in phi. So no fancy stuff there. But there is a 4-pi periodicity, but the 4-pi periodicity is not in phi, but it's in delta phi. It's in the flux through the normal region. These are the Fraunhofer oscillations. So the magnetic field is everywhere. So it's not just the gauge field, but it's everywhere. It's also in the normal region. So it's operative here. There will be a certain flux, delta phi. And you could then compare the periodicity of the critical current, let's say in the field where you're not in the quantum Hall effect, so weak magnetic field, let's say zero magnetic fields, where you would really expect a h over 2e periodicity, and then you would do the same effect in the quantum Hall regime, and this is what you would find. You would find that periodicity is now doubled. The periodicity is not h over 2e, but h over e. So this is, let's say, a 4-pi periodic Fraunhofer oscillations. That's how I would like to call them. And there's no way you can work around this. I mean, this will happen. There's no, I mean, with the 4-pi Josephson effect for the Majoranas, there's this thing about parity conservation. This is a much more tricky effect. Here, it's completely robust. Once you have a chiral mode, you must have H over E periodicity. And so that's the puzzle. And I will leave you with this puzzle. And I'm pretty sure Gleb will tell us more about this puzzle, that in the one experiment, the science paper by 2016, where they somehow, observed or found this supercurrent carried by a quantum Hall edge mode, the periodicity, this period doubling was not observed. So the same period in zero magnetic field was found in large magnetic field. So the same, presumably the same H over 2E periodicity, because in zero magnetic field, we definitely have H over 2E. And I have only one way to explain this, which is that contrary to what was somehow believed in the experiment, there is non-chiral transport. There could be a variety of reasons why there are other modes here along this edge, which are not chiral. And the moment you have non-chiral transport, then you're back to H over 2E. So that is, I think, from my perspective, the outstanding puzzle of the field. So I'm done. I think I have left 3 or 4 minutes, which I could either give to the next speaker, or if there's any question, I could entertain it now. Thank you.
Thanks, Carlo. Yeah, I guess since we have indeed a few minutes. So if there's any, say, clarifying, brief questions, maybe you from the audience, you could raise your hand and I would unmute you. Okay, we have one from Yorichi Ando.
Yeah, in this Andreev reflection, how should we consider spins?
Yeah, so this is important. So the things I showed you here is basically spin degenerate usual S-wave stuff. But you could imagine a spin polarization. Then you would need, of course, strong spin orbit coupling. If you have a spin polarized edge mode and there's no spin orbit coupling, then you cannot Andreev reflect from an S-wave superconductor. But if there's strong spin orbit coupling, you can. And basically, this phenomenology doesn't change. So you have the same H over E periodicity. The critical current is smaller, quite a bit smaller, because you need this spin orbit coupling. But that's it. Once you have strong spin orbit coupling, still a spin polarized chiral Andreev edge mode in one single spin will still be able to carry a supercurrent.
Okay, thank you.
We also have a question from Leonid Glasman. Leonid, I think you can unmute yourself.
Yep. Yeah, it's actually not it's a historic question. I think that actually, Carlo, from your review, I've learned about a paper which looked at the same thing, the skipping orbits along superconducting edge, which was on metals in 80s, perhaps TSOI et al.
Okay, Leonia, I mean, this was all. I haven't thought about these things for more than a decade, so I went back but I can easily stand corrected. This was one of the first papers I found. Certainly in semiconductors, I think that's the first, but it could well have been earlier work.
Okay.
All right, one more question from Ben Hunt.
Okay, there we go. Can you go to slide 3 for a sec, please? Right, so in the bottom left picture, it really depends on the details of the lattice, right? Because if you didn't know about the armchair or zigzag, you could deform the top picture into the bottom picture.
Certainly.
Is there are there any intermediate conductances that have to do with?
Well, okay, so this is this is Anton's theorem. Every edge is zigzag. So the generic thing, so zigzag, I mean, this was one of the early misconceptions somehow that you need a special orientation for zigzag. Any edge will be zigzag on long length scales. And so this is, I think, the generic thing. So what really matters is, are you covering a single edge? If you cover a single edge, then you go from a zigzag to a zigzag. That's nu1 equals nu2, then there's nothing. And if you cover two edges, then you will go from a zigzag to b zigzag, and then you have nu1 dot nu2 minus 1. I think that's the generic case. And the armchair is just some miserable thing which never happens. So the generic thing is zigzag case.
Yeah. Ben, that would be a great question to put into the HackMD document, and maybe we could have a more detailed elaboration on that in the discussion section, perhaps. So yeah.
Okay, thanks, Alan.